It's a great pleasure to welcome Graham Cormode from the University of Warwick. Graham is a professor of computer science and a research scientist at Meta. His research concerns data management, privacy, and big data analysis. Graham was awarded his PhD from the University of Warwick in 2002, and during his PhD spent a year studying at Case Western Reserve University in Cleveland, Ohio. He's previously been a researcher at AT&T Labs Research and at Lucent Bell Laboratories, focusing on network management. Graham was also the co-recipient of the 2017 Adams Prize for Mathematics for his influential work on statistical analysis of big data, and is a fellow of the Association of Computing Machinery. And today, Graham will give us a whistle-stop tour of differential privacy for data protection.
Right. Thank you very much for a wonderful introduction. Yes, I was given the brief. Can you talk a bit about differential privacy, a topic that the audience probably doesn't know, but it's been around for 20 years and has a few thousand papers about it. And make sure you cover sort of the fundamental mathematics underpinning it, as well as the applications. And I thought that's a great brief, because I know I cannot possibly live up to that. So I'm relieved of any stress. And I'll just talk around that theme for a while. Oh, yes, and the other additional constraints, of course, I'll be talking before lunch. So everyone is keeping an eye on the time. Good. So let's start by talking about privacy. And I think we've already had a bit of this discussion during the previous talk. So we're kind of up to speed with the idea that in the 21st century, we are gathering vast amounts of data about people as they transact their daily lives. And this data is interesting and valuable, and as a consequence, it's sensitive. Right? So all the information about your medical history, your financial situation, your likes, dislikes, physical activities, preferences, and so on, you know, paints a very detailed picture of it. And so naturally, we as a society have said, well, let's make sure that we think a bit about how we process and work with this kind of data. And so as a result, we have various regulatory frameworks in different jurisdictions that try to legislate how such data can be stored and processed. We have norms as a society as what we find reasonable and acceptable use of data. And indeed, we do have companies who make it their business to work with data and would like, perhaps for commercial reasons, to have a more positive approach to privacy. So the natural response to all these constraints is to say, okay, if it's so difficult and risky to work with private data, then we should just lock it up, encrypt everything, and pretend we never saw it. But then that goes against what we've heard already about how there is this value in the data, many positive applications, diagnostics, giving people advice, guidance. And so we'd like to sort of square this circle and say, well, how do we enable the positive uses of sensitive data without just casually discarding people's privacy? So that brings us back to this notion of privacy enhancing technologies, which again we've heard there are many flavors of different privacy enhancing technology that address different aspects of the problems that arise with working with sensitive data. And what I want to do here is try to draw this dividing line between security and privacy. Right? When I first started working with this topic, I used these terms almost interchangeably, but now I kind of make a distinction. Say, well, security is about controlling sort of direct access to data, so using the tools of cryptography and the like. And privacy is about saying, well, what do we learn from the data? So if we have done some data analysis and processing, what does the result tell us? in computational terms, and for my sins, I am a computer scientist through training, what does the output tell us about the input? So again, you can come up with scenarios where you look at the output of a computation, and if it's sort of a very direct, simple computation, it kind of tells you immediately things about the input. I tell you if my computation is add up to values x and y, and I report x plus y, and you happen to know or believe something about x, you can start to work out what you think y is. So again, it seems like a challenging question. How do you control what people might be able to learn from the results of function evaluation or computation? And the essence is to try and again make the distinction between, well, what we want to control really is what you learn about an individual. So we're implicitly here thinking of scenarios where we're taking in data from many individuals and producing a result that talks about their aggregation, the population behavior. So we want to enable learning about population or subpopulation behaviors, statistics, and be able to build models of those, while still trying to protect the individual. And that fits, again, many of the modern applications of data analysis. Okay, so I'm going to try and cover a fair amount of ground, and realistically, I may have to draw back on that ambition as we go. So I do want to tell you first some of the mathematical underpinnings about this particular formulation of privacy. So I'll tell you what differential privacy is and some of the basics around it. And then towards the end, I'll talk more about here are some of the ways in which it's being used in practice. So if we look at the history of how people have tried to think about privacy through a mathematical lens, there's a long and storied history which I can't do justice to, but drawing a sort of a cartoonish caricature, you can say, well, from the late 20th century through the early 21st century, various approaches were proposed that tried to say, we think you might be able to get some notion of privacy if you do this. Right. So there was a notion of sort of data swapping that said, see, you have a table of records of information about people. If you start sort of swapping values around, so I'll switch a couple of people's ages around, or switch over whether they're left-handed or right-handed. This sort of preserves core scale properties of that data set, but tries to sort of hide information about the individual. And other notions looked at things like, well, what if we try and make sure we take in some data set, we produce some output data set that follows some properties. So on the output, we maybe generalize things a little bit, fuzz things, censored or remove some information, so that on that output, any person that you might have in mind actually could be plausibly any one of 10 different records in the output. And all of these were plausible attempts, and all of these have, by and large, sort of fallen away. And the reason for that is essentially, they were vulnerable. You can think of this as an analogy to the early days of cryptography, when we came up with various simple cryptographic schemes, and then we learned by attacking and breaking these and coming up with stronger ones. Right. So essentially, these kind of techniques that try to perturb data in somewhat deterministic ways failed because these transformations were invertible. Not always invertible, but under certain conditions or in certain scenarios, you could reverse and learn something about the input that went into them. So around about 2005, 2006, this new definition of differential privacy was proposed. And what it tackled in some ways was it tried to reframe the problem. So if you sit down, without any sort of prior context, and you just try and work out what is it I would like privacy to mean? How would I try to come up with a mathematical definition of what it means to have a private processing or transformation of data? Quite often, the first few things you'd come up with is you'd say, well, I like to make sure that someone that looks at the results can't learn anything about what went into this process. And the problem with that is you're then trying to quantify over some unknown, unspecified adversary's ability to draw inferences. You're trying to protect against how someone might think. And the problem with people is that they come along and they have these beliefs and way of operating that you can't really anticipate. Right? So your notional adversary might have a set of prior beliefs that you think are entirely unreasonable, and a way of thinking that you think is quite unlikely, but when they combine them with what you produce, they may end up drawing a conclusion that turns out to be quite powerful and true. So it doesn't really benefit us to try and constrain or quantify over how an adversary might reason. So differential privacy, I think, rather deliberately avoids that framing. Instead, what it says is, okay, let's just try and look at what's the difference. So that's where the difference in differential comes from. Just try and look at what's the difference between what we might see as a result of performing this transformation, this analysis, depending on whether or not one particular person was present in the data. So it's trying to capture this notion that we would like to learn true facts or statistically true facts about the population, but not anything that speaks specifically about any one individual. So that attempt to draw a definition, and I'll progressively make that more precise on the next slide, is trying to make this, it brings with it some assumptions. Right? So it brings with it a view that when you're looking at a way of processing data, you're not looking at sort of a mechanistic, deterministic algorithm. You're actually looking at something that gives a distribution over possible outputs. That distribution is generated not from random variation within the data, because maybe you can't rely that there's enough necessarily entropy in the data, but it comes from your process being randomized. So it kind of moves you towards the notion that whatever data analysis you're doing, it should actually be a randomized process, and it should sort of bring its own randomness, not rely on external, not rely on randomness in the data. So moving towards the definition. So informally, what we're trying to say is we'd like to come up with algorithms. And again, another key property of differential privacy is it's not saying this is a procedure that you must follow. It's saying this is a property that a procedure that you might define. And as we go, we'll see many different such procedures. This is a property that a procedure might possess. So what we're saying is that the procedure that you run, the mechanism in the language of differential privacy, will produce an output distribution on possible outputs, and that output distribution should not change too much if you vary the inputs by contribution of one individual. So we can turn that into an equation. I'm reminded of the mantra that says, every equation you include causes your audience to halve. So I'm spending spending my equation budget carefully here. And then I go a bit crazy later on. But yeah, we have this sort of formal notion with a whole bunch of terminology that is basically trying to say the probability of seeing any event when you apply your algorithm to a particular input should look pretty similar to the probability of seeing the same event on a very similar input. So one could spend a lot more time on this. I'm going to be a little bit high level. So the key things to be watching for here are this notion of similarity is captured by these two parameters, epsilon and delta. So think of both epsilon and delta as fairly small. So e to the power epsilon is somewhat close to 1 and delta is somewhat close to 0. So if epsilon was exactly 0 and delta was exactly 0, it would say that all outputs are identically likely regardless of the input, which is a coded way of saying, you can achieve perfect privacy if you don't look at the data and you just output random noise. Which may sound faintly ridiculous, but is a good baseline to compare any proposed algorithm against when people say they have a solution that has some particular characteristics. Starting point to say, well, is it better than random noise? But in more general cases, epsilon is a small value, so it's saying that these two probabilities defined over seeing certain events look pretty similar. Delta gives you a little bit of extra wiggle room, but if two parameters epsilon and delta seem too much to carry around, then just pretend delta is 0 and focus only on the epsilon, which indeed many algorithms can and do.
Just to understand, you don't need a lower bound as well?
You don't, because essentially this is symmetric in these
I see, so that's
it's,
where it's defined like that.
Yeah, so it's a concise way, but you're right. You would like these two probabilities to be very close on both sides, and by the symmetry of the definition does actually require that. Good. So this is a nice definition. We can sit and look at it and appreciate it. As a computer scientist, I would also like to know, well, is it achievable? Does it actually, are there such algorithms which achieve this definition? So the answer is yes, there are very many, and so I'll try and give you a flavor of what they might actually look like and what they can actually do. So as I said before, a trivial way to satisfy this definition for any epsilon delta would also be to ignore the input and output random noise. So in other words, to get great privacy, but to not actually have any dependence on the input. So typically what we would rather do is say, well, how do we get something that does inform us about the input and the value of some function on the input without just being random noise? So one way to do that, so let's take sort of a canonical, simple objective. I would like to know within the population that consists of the people within this room, how many are left-handed? Okay, very good. So yes, let's say that is the thing that we want to ask, and let's further assume that handedness is now a sensitive personal characteristic which we don't want to freely divulge. Okay. So without privacy, you would count up how many people have this characteristic, and you would report the count exactly. With privacy, what you would say is, well, we're going to now have a distribution over possible answers. So there'll be some probability that I say there are 10 people in the room who are left-handed, some probability that there are 3 people in the room, and I'll pick according to the distribution that I define. So what I can do is come up with a distribution that meets that constraint on the previous slide, and then sort of under that constraint maximally keeps me close to the true answer. So if you follow that process, you can kind of write down a bunch of probabilities, a bunch of inequalities, and then either solve them or ask a computer to solve them for you. And what you get is you get a distribution that looks sort of like this. Right? You get a distribution that's peaked around the true answer. Here I'm constraining the distribution to give integral results. So let's say the true answer is 7. So there's some probability associated with 47, some with probability with 46, with 8, and so on. And if you plug in these constraints and then try and sort of maximize the probability that you give the true answer, what pops out is a rather nice symmetric geometric distribution. And what that means is if you sort of ignore things to the left, you get a geometric distribution. If you ignore things to the right, you get exactly a geometric distribution, but you're symmetric and you normalize in just the right way that this gives you the right probabilities. So what that says is, it doesn't have to be counting handedness; it could be counting any characteristic. So I have a technique to count that meets this privacy guarantee, which is basically compute the true answer. So assume that I'm trusted to receive your data. I'll compute the true answer on that data, add noise according to this distribution, report the result, and be done. So moving on from that sort of simple thing, if you start to look at the literature on differential privacy, you'll hear people talk a lot more about Laplacian noise and Gaussian noise. So Laplacian noise is essentially the continuous generalization of geometric noise. So rather than having discrete probabilities, you have a continuous distribution, symmetric around the true answer. And Gaussian noise, people like their Gaussian distributions, and indeed there's much work that precedes differential privacy that was trying to achieve some notion of privacy that tried to understand what would happen if you added Gaussian noise. So indeed, you can add the right kind of Gaussian noise as a function of these parameters epsilon delta, and you will obtain the right kind of differential privacy guarantee. Okay. So I'll try and speed up a little bit, I hope, without losing too many more of you. This is where the equations start coming thick and fast. So what I talked about with this construction for geometric or Laplacian or Gaussian noise was an approach that makes sense if I'm just trying to count discrete quantities. But again, in life, there's more than just counting. There's all kinds of functions that I might want to evaluate on data and report that would give meaningful statistical insight into the data. So a generic approach is basically to say, well, the same kind of idea works, which is I can meet the differential privacy guarantee by computing the true answer to my function on the data, then adding the right kind of noise, and it's usually noise again from geometric, Laplace, or Gaussian distributions. And the question is just how do I scale the noise so that I meet this particular property that I needed a few slides ago. And a quick answer is we'll scale the noise based on how much your answer can change. So if I change one part of the input, if I can add or remove an individual, how much can my answer change? That basically just gives me a scalar multiplier for how much noise I need. And sort of the essence of one of the reasons that differential privacy got off the ground and was a definition that people felt they could work with is that for many common functions, this scaling factor is not too big. So we said that if I want to count, then essentially it's a scale factor of 1. If I want to compute a histogram, it says how many people fall in certain different buckets based on their characteristics, that has a scaling factor of 2. Because if I change your characteristics somehow, if I replace you with someone who differs, then that essentially moves. It takes a minus. In the worst case, takes a -1 for the bucket you were in and a +1 onto the bucket that this new individual resides in. So this starts to give a recipe, rather than saying we have to look for every individual function and kind of from scratch figure out how to turn it into a differential private algorithm. This gives a slightly more generic recipe for a class of numeric functions. Not everything, and clearly there are many functions of interest for which this kind of essentially sort of a Lipschitz bound is large, and that then generates a whole line of work within differential privacy saying, well, what are some other ways that we can usefully obtain information about such functions? Another consideration is what I described so far. Says here's what you do if you're trying to output a numeric function, right? You evaluate the numeric function and add numeric noise. What if I'm trying to evaluate a function that has categorical outputs? It picks from a collection of possible outputs. So along comes something called the exponential mechanism, which I will speed through, but basically it describes a way to construct a probability distribution over possible outputs, where essentially you sort of take that high level idea from the numeric case, which is you would prefer to output something which is as close as possible to the true answer. It asks you to bring some function that gives a numeric evaluation of how close a potential output is to that desirable answer, plugs that in, and then defines a sampling distribution. So I'll skip that. So this is starting to say, here is this notion of privacy. Here are a couple of ways that we can achieve that definition of privacy over certain categories of questions you might ask. Then the thing that really turns this into a more powerful tool is to say, well, what if I want to think about not just counting how many people or building a histogram or sampling some single value. What if I'd like to take an existing non-private algorithm that clusters some data or builds a machine learning model, and I would like to think about what would it mean to make a differentially private version of that procedure. Naively, I might think, okay, well, I've got to sort of, for every single possible algorithm that I might want to study, I'll have to come up with a bespoke analysis of exactly how does the output of that algorithm depend on its input. And you can easily imagine that for today's modern data analysis and machine learning algorithms, this is not going to be a particularly convenient task. So what makes our lives a bit easier is that there is a sort of a theory built around differential privacy that says, here's how you can reason about composition. That is, if I do one step of procedure, which in isolation achieves a certain level of differential privacy, followed by another step that does something different, and then again in isolation achieves a certain level of differential privacy. If I do step 1 followed by step 2, that whole procedure then also has some differentially private properties. So you can imagine, step one, I had some parameters epsilon 1 and delta 1 that described their differential privacy. Step two, I had epsilon 2 and delta 2. And cutting to the chase, essentially what happens is, for a first sort of simple result is you can just add those epsilons. So it says you can start to think of this parameter epsilon, which remember was sort of describing how close, how close to probability is that we're describing properties of the output were. You can start thinking of this as a resource, but as you're producing some data analysis procedure, you're effectively spending this epsilon. So you would like epsilon to remain at the end of this total procedure to be moderately small still. And then each step you spend a small quanta of this sort of privacy budget that we've come up with the notion of. And at the end, you can sort of make some statement about the whole procedure as you compose over all of the individual steps. Right. So essentially, first process is as you take multiple steps of data analysis, this meter that's tracking your privacy expenditure is sort of racking up linearly. You're summing up these epsilons. What you quickly find as an algorithm designer and algorithm analyst is it's very easy to sort of blow your budget. It's very easy to kind of look at a moderately complicated procedure. Say it's training a machine learning model, and end up with a bound that looks vacuous. That you get some huge number here, and remember, epsilon is basically constraining a ratio of probabilities in the exponent. So it's an e to the power of epsilon. So you get some number that says, okay, you've spent 100 units of privacy, which says that as you change information about one individual, these probabilities are bound in a ratio of e to the power 100, which is sufficiently large as to be meaningless. So what we then go on to do is say, firstly, can we come up with algorithms that are much more cautious in how they access the private data? So you start to see that accessing private data is a resource over which to be frugal. And can we come up with tighter ways to reason about the overall behavior of this composition of steps? And there's a more sort of advanced theory and many more sort of subsequent analyses that say, rather than having this sort of linear composition, the true behavior is more sublinear. So essentially, if you do it k times, rather than giving you a leading term of k times epsilon, you'll get something that's more like the square root of k. It gives a bit more control over this behavior. Good so far. Okay. And finally, on the technical side, I think I'm not going to say too much about this, but just to kind of give a hint that, again, most of what I've talked about so far is the initial exploration of differential privacy. In the subsequent years, there's been so much work defining variations of this and looking at different ways to characterize and describe what it is that this seemingly simple definition is actually describing. So there's ways to reframe this whole notion of privacy into something called a privacy loss random variable, that is basically looking at sort of log odds ratio of seeing certain events and then tracking this over multiple steps. So looking at ways that you can frame this as a random variable and see how that random variable kind of spreads and grows over subsequent steps of computation. So I think that's probably more than enough of some of the underpinning mathematics.
Can I just ask a question?
Please do. Yeah.
Does the sample size make any difference? You haven't really talked about how many.
Good. I'll probably allude to that in some of the applications. But yeah, so the question is, what about the sample size? So the sample size has a significant impact on how useful the answer is that you get in the following sense. So we sort of, the way we as privacy researchers tend to approach this is we say, well, privacy is absolute in the sense that we will ensure that whatever notion of privacy that we choose to adopt is always met. So what does that mean? So if you go back and sort of look at the first ways of achieving privacy that I talked about, it's basically with noise addition. So if the sample is small, if there's two people in the room and I'm asking this question about how many left-handed, and then I add some random noise to that, that random noise essentially completely obfuscates any useful result you might get. It does so as a function of epsilon, so you might choose an epsilon that is sufficiently weak as to still preserve good information. On the other hand, if I ask for a population of a few thousand people, how many need these characteristics? The magnitude of noise that I add depends only on the influence of an individual, not on the size of the sample. So inherently, I get a much more accurate, relatively accurate response. So you could argue this is sort of the way in which this notion of privacy interpolates between the two notions from the start of seeking privacy for the individual, but sufficient meaningful accuracy for a larger population.
Sorry, can I ask a quick question? So if I understood correctly, the sort of analysis you do of composition concerns different calculations from the same data set. Do people think about situations where the same data point is contributing to multiple data sets?
Right. So what you've hit on there is one of the fundamental challenges of going from this nice clean definition into a strong real world kind of guarantee. So what we said through these techniques of composition and more generally a notion that's referred to as privacy accounting is to say, as I look at an algorithm that analyzes the data of one individual, I can kind of track via these parameters epsilon delta some notion of privacy loss. And I can give some sort of intuitive bounds that say, if epsilon delta will fall within a certain set of ranges, we consider this stronger privacy. And as epsilon in particular gets larger and larger, it degrades to being not meaningful privacy. And this is great if you look at a single algorithm that analyzes the impact on a single individual. As we navigate the world, we are subject to immense levels of tracking and data reporting, possibly from the same agency, possibly across multiple agencies. And you could try and say, what's my global privacy status? And again, we would very quickly sort of fall into this notion of something that is so loose as to be perhaps meaningless. So again, this is sort of where the theory and practice must diverge. And so within the practice, which I'll talk about in a subsequent slide, people do what they can within a somewhat blinkered view of saying, well, if this was the only way that we looked at the data, then we would have this somewhat meaningful guarantee, and outside of that, all bets are off. But we're sort of back in the situation that was maybe alluded to during the first talk of saying, well, something is better than nothing. Doing data analysis that is privacy aware is perhaps preferable to doing data analysis that is indifferent to privacy. And indeed, so the first set of applications I'll refer to come from those big tech titans that we've talked about before. So over the last decade or so, Google, Apple, Microsoft, Snapchat, and others have proudly trumpeted their great efforts in deploying privacy-preserving data analysis, and maybe been much more quiet about all the other ways in which they interact with your data that is not so constrained. So maybe the hope or the goal is to say, rather than sort of resign in frustration, that we would just hope to see privacy preserving data analysis and privacy preserving machine learning become more widespread. So we do at the moment have to sort of pick on these sort of examples, and I'll talk in a little bit about how Google in the Chrome browser was tracking information about people's browsing activities under this model of privacy. The other example that's often mentioned that I don't talk about here is a few years ago in the United States, the 2020 census adopted differential privacy to report certain of their data products. And this was driven in part by looking at previous data releases, analyzing those and saying actually they were leaking quite significant information about them. When you look at census tracts that go down to fairly small groups of dwellings, that you can make some pretty strong inferences about individuals and their characteristics. So differential privacy was incorporated into certain but not all of their data releases to try and moderate that. So I like to kind of dig in a bit and say what exactly is going on. So what did Google do? And this is somewhat outdated in that this is what they were doing 10 plus years ago. It's not what they're doing today. But the way they want to collect information, so that essentially the challenge that Google faced is they wanted to report information over a very large, almost unimaginably large domain of possibilities. So think about the number of possible pages on the World Wide Web that you might visit. And they want to collect certain statistics about those, mostly I think for the purpose of identifying malware and bad behavior on the web and being able to kind of alert users to that without directly collecting their browsing behavior. So the sort of the technical heart of their idea, I can describe it to you in one line. It was to apply randomized response to the bits and blue filter. And if you know what randomized response and blue filters are, that's completely descriptive. And if you don't, it's largely opaque. So for Bloom filter, think of this as basically just a very compact way to encode in binary information about membership or non-membership of a set of possibilities. So a very short way of capturing a small subset of URLs and that. And randomized response is a statistical technique going back to the 1960s, which essentially takes those bits in the binary representation and either reports them truthfully or with some smaller probability flips a 0 to a 1 or a 1 to a 0. And as we who have activities in academia are approaching the next edition of the REF exercise, I always like to think of this as one of my favorite examples of academic impact. Because this was technique designed in the social sciences as a way of essentially eliciting accurate statistics about sensitive behavior. And here's an application that took only 50 years to come to fruition. But yes, so it was sort of a good first attempt. Had some sort of limitations. So a few years later, Apple came along and published a nice white paper that described what they were doing in a similar application. So within the Apple application, they were also trying to track statistics on how frequently people use certain emojis, how frequently they use new words that weren't in the dictionary in their texts, and my favorite application, how frequently they would go to a website and immediately hit mute because it was playing some obnoxious music, and trying to use that signal to say maybe we should preemptively mute those web pages. So it's one of the few cases, it's a few years ago now, where if you watch one of those glossy Apple keynotes where they say, here's our new exciting technology, a new phone system that's got so many megapixels, there was a slide where differential privacy was held up in large writing as a wonderful new technology. And just to sort of give you a flavour of sort of technically what was going on within that, it sort of looked similar to the Google approach, but with a few extra twists. So instead of the blue filter, we used a sketching technique, actually one that I was involved in creating. Instead of directly reporting these noisy bits, it used some tricks involving discrete Fourier transforms to kind of take a sparse signal and spread it out in the transform domain, and therefore just have to report sort of samples from the Fourier domain. That was a nice technical trick. And that then enabled this kind of data reporting. Any questions? Good. Okay, that was application one. So we've already heard this phrase, privacy preserving machine learning or privacy aware machine learning today. So we can think about how you might use more encryption to do this kind of privacy preserving machine learning. You can think about how you might use a notion of federated learning we heard very briefly about earlier. And you can think about how differential privacy might play a part. And maybe the one important point I'd like to make about the plethora of privacy enhancing technologies that we'll hear about today, and the many others that we won't hear about, is that these different technologies are not necessarily in competition with each other. They are often addressing different aspects of how you formulate privacy. And in particular, there are many constructions, particularly as we move towards these kind of deployments, that don't pick one, but pick multiple privacy enhancing technologies and seek to use encryption or even homomorphic encryption for one phase of the computation, but introduce differential privacy noise in addition in order to get some stronger sort of defense in depth notion of privacy. So one of the challenges with machine learning is it's a big, complicated area, very active, and there's all this new buzzwords and terminology. We've heard a bit about neural networks, and people start talking about transformers and attention and large language models. And as a mathematician or computer scientist or statistician, you feel, how do I keep up with this complex area? Well, one of the nice aspects is sometimes you can be agnostic about what's going on in these neural networks. Because a key part of machine learning is training, is saying, given some data, given some architecture of a neural network, choose the parameters, choose the numbers that are going into the neural network that, given the data, the training data I have, that minimize some loss function. And this is a suitably generic and abstract problem that you can then just focus on that training step. And essentially, with some oversimplification, all training of machine learning models is done using variations of stochastic gradient descent, which say, I've got a function that's defined by the data of my current set of parameters that I want to minimize. And I essentially sample some examples from my training data, see how well they do, basically interpret the results as a gradient and push that back to tell me how to change the parameters. And viewed from that arm's length perspective, this means that machine learning training is a problem that you could start to think of as one algorithm for which it would be very valuable to provide a private version. So glossing over all of the detail which I've conveniently ignored, you can kind of then say, actually, and the algorithm isn't that difficult. Like the algorithm looks at the data, so it's definitely incurring some types of cost, but produces these gradients that I want to apply to the parameters, which is basically a vector. So in essence, I just have to figure out, well, how much noise do I add to the gradient vector to provide some notion of privacy at each step. And then I do that over all the steps, and I reason about how many steps have I taken, what does the impact mean for this differential privacy characterization in terms of this parameter epsilon. And that is almost how you get a differentially private stochastic gradient descent algorithm. The main tricky thing is clearly the relationship between changing the input and the effect that has on the gradients that are telling you how to update your model is highly nonlinear, highly hard to reason about. So you apply the trick that says, okay, well, I'll just force that the vector that one step of this process gives me has bounded magnitude. So maybe the vector is saying, send your parameters of your model way over there. I'll just say, well, I'll just kind of clip that so it has norm 1. So maybe I'm not moving as quickly in the direction of improving the model as I'd like. But because I know it has bounded norm, then I can plug it into that framework from before that says you can add noise to an algorithm based on this maximum sensitivity, the most that a value can change. And you will obtain some kind of differentially private notion of machine learning training. So where this stumbles is the same issue I've alluded to before, which is because this is an algorithm that typically iterates many hundreds or thousands of times over the training data, your odometer of privacy is racking up, and you end up with some value that looks like thousands, and as we've said before, this is not really meaningful in any particular sense. So where folks have gone beyond that and given privacy guarantees that if not thousands are maybe down to tens or below, is by focusing on this specific task and saying, how do we really tighten our understanding of this generic but widely used algorithm, and in doing so introducing some new tools for the analysis of algorithms. So there's a flavor, one piece is just understanding the interaction between subsampling and privacy. That has a natural kind of amplification effect. And another has driven this area that I referred to as privacy accounting. So coming up with new ways of tracking how much privacy budget are you actually expending on this particular task. Which has then got to the point that there are now libraries you can download that operate either within PyTorch or within the TensorFlow environment. And with a few lines of extra code, you can turn an existing training algorithm into a private training algorithm. Again, some companies are choosing to do that. Again, I think Google has been quite vocal about how they've been applying differential privacy to training of some subset of their algorithms. I'm going to skip over that, but can come back later if we hit on those questions. And finally, I want to talk about third application. We talk about basic statistics and machine learning modeling. So the last task, which sort of sits between those two, is thinking about synthetic data. So in some ways, synthetic data is often positioned as a privacy-enhancing technology in its own right. So the idea of synthetic data is to say, real data comes with all these burdens. Right? It has very sensitive information within it. There are maybe constraints on how it can be used, either legally or within an organization, policy constraints. Wouldn't it be easier if I could just get some fake data that kind of looks like the real data, and then if the fake data was sufficiently distanced from the data that inspired it, I can just go to town and do whatever kind of ad hoc exploratory analysis, build what kind of models and like and so on. So the challenge there is, how do you still actually have a privacy problem? How do I generate realistic synthetic data that is inspired by real data but doesn't simply duplicate it? And what you quickly realize is that synthetic data is not really a panacea. It's actually another instance of the same problem that we've been looking at so far. Right? Synthetic data is really a data modeling question, saying how do I build a model of my data and instantiate its parameters in such a way that I can use this as a generative model to create lots of examples of synthetic data. Think of a problem where we have some input data in the form of a table telling about individuals, their preferences, their physical characteristics, and so on. What we'd like to do is figure out what's an appropriate model that we can build of this, instantiate, and provide a formal differential privacy guarantee for. So one example is a piece of work that I was involved with, again, 10 plus years ago, that was trying to sort of figure out what's the right trade-off here between the descriptiveness of the model that you try to build and its privacy properties. So clearly, the more descriptive the model is, the more parameters it has, the better it can describe the data. But the more parameters it has, then the more uncertainty and noise you need to introduce to those parameters if you want to meet the differential privacy guarantee. So we kind of looked at this, and we looked at different flavors of models, and we said, well, actually, as a starting point, a Bayesian network is a nice model, something we can understand, where it lends itself very easily to sampling if we can instantiate the Bayesian network. And so then that gives us this sort of technical challenge that says, well, how do we, under this notion of privacy, perform this kind of data modeling? So in essence, a bunch of questions, some of which were easy. So things like, once you've actually chosen what model you're going to build, then instantiating the parameters of that model is kind of reduces to one of the first things we looked at, which is it's basically a histogram question. You're counting how many individuals have certain combinations of features. So the harder piece is then doing this kind of modeling of the correlations and deciding effectively what graph to draw. Okay. So in this whistle-stop tour, I tried to give you a flavor of how we got here, what this differential privacy definition is trying to describe, how it can be instantiated, and then some of the applications across tech, across national government statistics, how it's being used. And I can then point you to the much broader literature, but still there are vastly many questions people are still asking about how do we square this circle between private data analysis but getting useful results, as we're interested in more and more complex functions of data, and we want to make these tools available to a broader audience. Okay, so I'll stop there. Thank you so much for your attention.
Thank you very much, Graham. Are there any questions either in the room or online, Graham? No, I might ask.
Go.
So there's sort of popular bits of research around sensitivity of the individual. That I can easily think of cases where small communities might have their own sort of notion of privacy.
Yes.
Everybody on the street has the same dietary has a tendency towards the same dietary restriction or various things for that. Given that all the sort of major applications focus on the sort of individual, and there's a sort of a composition result that sort of says we get a certain amount of subgroup protection for small subgroups.
Good, yes. So you'll be pleased to know this question has exactly been formulated, and I won't say fully addressed, but essentially the way it's described in literature is a notion of group privacy. So like I say, if there is a small group of individuals whom you might then treat as a unit, how does their privacy interact with this individual-based notion? And the short answer is, for this kind of group privacy, you get that sort of simple composition that says if there's 10 people in the group, then effectively their group privacy is 10 times worse than if there was one person. What's interesting is that that's kind of where that has stuck. So it's somewhat an open question to, again, understand this notion of group privacy. There's sort of a baseline result, but not really much beyond that.
So what we see is you start with, let's assume we want to calculate a given function of data, the mean, and then we're going to add noise to the data.
Yeah.
You might do better by changing functions slightly.
Yes.
Like a twins mean is going to be less sensitive to
Absolutely.
Is there another side of this?
Well, so I didn't. I'm keeping it short because I think we're all going to want to get to that. Yes, exactly. And some of the things I touched on kind of did that. So the differential private stochastic gradient descent effectively changes the function, right? It wants to follow the gradient all the way, but we change it to say we're going to bound it for this process. We don't always add noise directly to the data. We often think of it as adding noise either to the full result of evaluating functional data, or sometimes an intermediate result, which we then combine. So there are all these sort of tricks to say, sometimes we change the algorithm to get a good result, sometimes we change the question. Yeah, absolutely.
Okay, so maybe we can leave more discussions for over lunch. Let's all thank Graham again.